If you're studying the kinetics of a unimolecular reaction, there's another way that you can get the order of the reaction and its rate constant a little bit less accurately or a little less precisely, but nevertheless a good way to go because it's very quick. Let me describe what that is for you. Okay, so in this case, we've got the half-life analysis involves looking at the half-lives for various orders. Now I'll remind you that these are results we got before when we looked at the integrated rate laws for these different orders of reactions. And these are what we're going to use. Now as we look at these things, we can interpret them as follows, that this T1/2 for order 0 actually increases for larger A0. So as A0 gets greater, the half-life would also get greater. I'm going to go over to the other side. For order equals 2, it gets smaller, so it decreases for large A0. And in between, we have for order equals 1 that it stays the same. And we remarked on these things when we did the integrated rate laws, but we're going to actually take advantage of that in this particular treatment so that we can figure out what the order of a reaction is. All right, now we can use these a couple of different ways. Okay, one of the ways we could use this is we could do a long time measurement of our concentration as a function of time. Okay, and when we do this, what we're going to do is be able to look at more than one half-life for this decay process. So this is something I'll call successive half-lives is what we're going to focus on. Another way we could do this, though, is if we want to look at shorter time data, so short time measurement, we would do this maybe for several different trials, each of which has a different initial concentration. All right, so this one is one where we're following the same trial for a long time. This is one where we might run a couple of different trials and just see how the initial concentration may affect the length of the half-life. All right, so both of these can give us a clue as to what order reaction we're looking at. So let's look first at the successive half-lives method. All right, when we have a lot of data for A of t, that means we can draw that out and take a look at what that time dependence looks like for A of t. And I'll say that we know that the order 0 is a linear plot. So let me write that up here, linear plot, whereas both of these two, order 1 and order 2, are exponentials. Now, order 1 is an exponential, I'm sorry, they're decays, not exponentials. Order 1 is an exponential decay, and order 2 is a 1 over a decay. They're not always easy to tell apart when you just look at them visually, so that's why we need to do a little bit of analysis. All right, but I'll remind you that in the case of the first order reaction, when we look at its decay as a function of time, so up here will be our initial concentration of our reactant. We're going to have a decay that comes down like this, and it approaches 0 relatively quickly as it goes down. But the key point of this is that when we get down to this 1/2 point, we'll be able to read off the half-life for the initial thing. When we go down to the 1/4 point, this is the second half-life, we'll find that the second half-life will simply be occurring at twice the initial half-life. In other words, this time gap and this time gap are the same for a first order reaction. So what this tells us is that the first and the second half-lives are going to be equal to one another. Okay, so this is a very characteristic feature of first order exponential decays and is pretty easy to spot if we have long time data. What about if we had a second order reaction? Well, in this case, we'll again have something that decays, and it looks something like this, but it will have a decay that again starts at our initial concentration, and it'll come down fairly sharply, and then it will level off, and it takes a long time to get down to zero. So in this case, when we look at the different half-lives, it will look something like this. So here's our point at 1/2 our initial concentration. It comes over, and we have our first half-life here. And then when we go down to half of that, so this is 1/4 of our initial concentration, and come over, we have to go somewhat farther out before we go there. And in fact, this gap here, you can show mathematically that this second half-life is actually equal to twice the initial half-life. This should be 1 in parentheses. All right, so we've gone out to, so this is our first half-life, and this is our second half-life, which is at 3 times T1/2. 2 in here and 1 in here. All right, so this is actually a pretty easy thing to spot if you've got reasonable quality data. In fact, I would say that many times you can determine this just from a cursory inspection of the numerical data that you're given. You don't have to do a long fancy analysis, just look at the data and see if you can see where the first and second half-life occurs, and if they're occurring at even intervals, then this is what you have as a first order process. If the second one is farther out by quite a bit, then you're looking at a second order or even higher order process. All right, so how would we use the second of these methods to to use half-lives to determine a rate order? Well, let's once again, I've got the results for the half-lives written up here, and in essence, what we're going to do in this case is we're going to measure the first half-life. So we're only measuring. So we're measuring our concentration up to the first half-life. But we're going to do this for several different initial concentrations. Okay? And these equations up here tell us exactly what to expect when we do that. And I'll say that there's really only 3 possibilities. I mean, obviously there could be a third order equation, and that would be something a little bit different. It'd be probably very similar to the second order one. Okay, one, we would find that all of our trials, no matter what the initial value of A, all trials result in same value for the half-life. Okay, what is that going to be? Well, it has to be order 1, because order 1 has a half-life that does not depend upon the initial concentration. Okay, for the other 2 possibilities, we would find that for larger values of the initial concentration, if they have longer half-lives, in other words, half-life increases as A increases, this is indicative of a 0th order reaction. All right, what if they get shorter? Well, I think it's pretty easy to tell. If larger A gives us shorter half-lives, then this is going to mean that we have a 2nd order kinetics going on. And I should have probably written up here that this means a 1st order process. All right, so these actually represent really quick and easy ways to determine the order of a unimolecular reaction. I will say that you dare not use them when you have something higher than a unimolecular reaction, because the interdependence of the 2 concentrations or 3 concentrations of the reactants will skew the results, and it won't give you an accurate reading. But these will both tell you very quickly what the order of the reaction is for a unimolecular reaction. I'll also mention that once you know that it's 1st or 2nd or 0th order reaction, you can then use the integrated rate law to determine exactly what the rate constant would be using your experimental data. So this is a great quick way maybe to get to an answer. So if you're doing an experiment in the lab and you want to quickly know what the rate order would be and what the rate constant might be, this is one way you could do it.